he will speak about magnonics and optomagnonics with ultracold atoms.
Great. So first of all, thanks everybody for allowing me to speak from afar. And I know I'm missing out on inverted caipirinhas tonight, and also a plate full of shrimp for dinner. So that's my bad. Hopefully the connection will be good enough for me to be able to share with you some of the research we've done at Berkeley insofar as it pertains to the topics of this workshop, which is looking, for example, at small systems that are undergoing non-equilibrium quantum dynamics through a quench, and the dynamics of how strong correlations are formed. Let me see. I should switch. Okay, so the focus of my talk is going to be on aspects of magnetism as they're realized in ultracold atomic gases. And let me just start off by describing what one could mean by magnetism within these systems. First, let me point out that a lot of the atoms that we choose to work with in our cold atom experiments have a spin degree of freedom as an internal degree of freedom of the atom. So here I'm showing the example of one of the workhorse atoms within our field, which is one of the alkali atoms. And if I look at the net angular momentum that it possesses, being the sum of the angular momentum of the electrons and also the angular momentum of the nucleus, then altogether in the electronic ground state, I have different possible total spins of the entire atom. That's shown here, where the total spin can be either 1 or 2. And within each of those manifolds of states, of course, there's many magnetic sublevels. So magnetism can, to some degree, just pertain to ordering in terms of the magnetization that is displayed by these internal states. And that, in fact, is going to be the magnetism that is referred to in pretty much all of my talk. Half of my talk will concern the physics of what are called spinor Bose gases. So that's a name we've given to quantum gases that are allowed to occupy all of the magnetic sublevels with a given total value of the atomic spin. So, for example, that can be a spinor Bose gas with a net spin of 1 per atom, or as I will discuss in the latter part of my talk, they happen to be gases with a net spin of 2 per atom. So there's been, a lot of work. I won't summarize all of it in terms of understanding the magnetization order and dynamics within these kinds of spinor gases in several different atomic species. But you also should be aware that a lot of work on magnetism in quantum gases actually has nothing to do with spin and nothing to do with real magnetism. But it makes use of the fact that we can cleverly represent spin in terms of some other degree of freedom of the system, and in particular maybe degrees of freedom that have to do with the center of mass motion of the atom altogether. So, for example, there's a number of works that are coming online now where people work with an optical lattice potential. So that's a periodic potential formed by interfering laser beams. And now the pseudo-spin degree of freedom can have to do with where the atom is located within that the unit cell of that lattice. So if you will, this is kind of like the pseudo-spin degree of freedom that applies in graphene, which was the subject of your previous talk, where an electron can reside in either the A or B sites of graphene, and it's useful to consider those as being a pseudo-spin degree of freedom. The same game is being played in atomic physics now as well. Another set of really intriguing experiments, hopefully this isn't in your way, has come from experiments where one can artificially create a band structure that has a degeneracy in momentum space. So this diagram here refers to experiments that are going on in Cheng Chin's group at the University of Chicago. And I urge you to look at the papers that are published by that group. They have a lot of gorgeous results having to do with non-equilibrium quantum physics, some very detailed data on scaling and the Kibble-Zurich mechanism, and they're really leading the charge in that area of research. And the way they implement their scheme is they're able to turn the dispersion relation of the gas from having a single minimum to multiple minima in momentum space. And given the nature of interactions between atoms, that can drive a pseudo-ferromagnetic phase transition. But actually, what I will tell you about has to do with the real magnetism of these atoms and the physics of spinor-Bose gases. So the first set of things I'd like to tell you about is what now is some rather old work, but where we, I guess, initiated the study of quantum quenches within cold gases. Gabriel earlier today, I think, showed you a slide that summarized many different experiments that have been done on quenches both across quantum phase transitions and across thermal phase transitions in cold gases. So I'll tell you a little bit about our contribution to that story. The physics we're going to explore here is something like the physics of the transverse spin Ising model, but actually in the sense that we have a something like a bias field that can preclude magnetic order, which competes against interactions that enforce magnetic order. So this these interactions have the following nature. You can, the physics in these alkali atoms in particular, the nature of interactions is that they are short-range contact interactions. And the contact interactions have some spin dependence. So we can imagine a collision where two atoms come into a collision in particular spin states, and after an interaction they emerge in some different spin states. We could potentially have a very difficult problem of trying to understand the strength of all of those kinds of interactions, all the different input channels and all the different output channels. But in fact, because of the spherical symmetry of the problem, the fact that these states are all, after all, different projections of the same angular momentum, it turns out that these contact interactions have a very simple form. There's a scalar form of the interaction, which leads just to an overall repulsion between atoms. And there's a spin-dependent form, or spin dependence of this interaction, which adds a repulsive energy that can be either larger or smaller, depending on the spin state of the atoms. And it's that modulation of the repulsive interaction between atoms that leads to a form of magnetic ordering. And in particular, for rubidium, we find that this spin-dependent interaction encourages all of the atoms to be magnetized in the same orientation. I'll get to that in just a second. In addition, of course, these energy levels are influenced not only by the interactions between atoms, but also by any magnetic fields that we apply to the system. So, you know, the first culprit to influence our system would be the linear Zeeman shift, which is just due to maybe a background magnetic field that I apply either advertently or inadvertently to my system. This typical magnetic fields in our laboratory are of such a large magnitude that a gas, if it were to equilibrate in the presence of that magnetic field, would actually very trivially magnetize itself with all of the atoms being in one particular magnetic sublevel, because the interaction energies, the temperature, all the relevant energy scales in the atom are typically very much smaller than this Zeeman splitting at any reasonable magnetic field. What is very fortunate, at least in my research on alkali atoms, is that the collisions that are required for relaxing in the presence of a magnetic field are very rare in rubidium. This is because the magnetic moment of rubidium is very small. And so it turns out that because the atoms can't undergo these Zeeman relaxing collisions, they actually equilibrate in the presence of a constrained Hamiltonian, which is one as if the linear portion of the Zeeman shift has been eliminated altogether. So that conservation law really saves our ability, it gives us the ability to do interesting experiments even with reasonable experimental conditions. There is one more effect of the magnetic field, however, that does apply to these gases, which is there's a quadratic Zeeman energy, which regulates whether, for example, two atoms in the m=0 state should undergo collisions that redistribute the atoms in the +1 and -1 magnetic sublevels. So for this spin-1 Bose gas that I'm talking about, there is a collisional process that changes the population of magnetic sublevels, which leads to interesting magnetization dynamics. And it's governed by the magnitude of this quantity here, Q, the quadratic Zeeman energy. If I pull together now these two relevant energy scales, the interaction energy, which has its spin dependence, and this quadratic Zeeman energy, which is something that is applied experimentally, we can derive, let's say, a mean field energy functional, which is written up here at the top of the slide. And it has two contributions, and this is where it is like the transverse field Ising model. Here's the effect of externally applied single particle energy scales. And if they're large enough, if this quadratic Zeeman energy is large enough and positive, it will polarize the entire quantum gas to be in the m=0 state, which is now very strongly favored energetically. Once we suppress the single particle effect, then the two particle effects or the interaction effects come into relevance, and this term now dominates the physics. In the case of rubidium, as I've been implying, this term encourages ferromagnetism, with all of the atoms being oriented with their magnetic moment in the same direction. And so we expect there to be a transition from a state here that shows no magnetic moment to states here at lower values of the quadratic shift that do show a magnetic moment. And those states, of course, are characterized by different broken rotational and gauge symmetries. Whenever we have states, of course, with different broken symmetries, we expect transitions between them. Those transitions occur at 0 temperature and also at non-zero temperature, as shown in the diagram now. And so we can do experiments where we probe either crossing the thermal phase transition, as shown here, or crossing a quantum phase transition when the experiment is done at sufficiently low temperature. So this spinor Bose gas system has therefore become a real playground for looking at the physics of quantum quenches in both simple and complex systems. I will focus on this quantum quench experiment, which is now somewhat well known in the field. I should tell you how it is we make our measurements. The experiments, so here's, you guys are in Brazil right now, so you recognize this picture. The experiments are conducted with atoms that are in a geometric structure that is surfboard shaped. So the atomic gas is typically very thin in very thin in one dimension and quite extended in the two orthogonal dimensions. We measure these atoms by passing light through the thin thin direction of the gas, and therefore we obtain a projection image that determines the two-dimensional distribution of atoms in the plane, in the widely imaged plane. And I'll tell you a little bit about this later, but we can use both optical birefringence and also sort of a spin-dependent selectivity of microwave pulses to take a number of these projection images, and from them we can reconstruct, in this integrated profile, we can reconstruct the spin state of the atoms with high spatial resolution. And so, for example, we obtain the following. So these are data that are taken where we characterize a gas. Here's one of the gases, here's another one, so forth, on separate repetitions of the experiment. So each of these images shows a different repetition of the experiment. For a time that varies after we've suddenly quenched a system from that paramagnetic phase into the ferromagnetic portion of the phase diagram. And we expect that after such a rapid quench, the system should develop ferromagnetic order, which is now favored energetically. And we find indeed that it does so. So these images, they show the transverse magnetization of the gas, where the direction of the transverse spin is indicated by color, and the magnitude of the transverse spin is indicated by brightness. That's our way of displaying this two-dimensional information visually. And as a function of time after the quench, the gas indeed acquires a strong degree of transverse ferromagnetic order. And you notice that this order, of course, is established very inhomogeneously. Within this gas, you see regions where there's a common value of the spin. There are other regions where the spin varies rapidly in space. And this is because we have a transition across a symmetry breaking phase transition that occurs rapidly and therefore inhomogeneously in space. And so this is the image of what happens after this quenched object evolves and coarsens for some period of time. So, you know, the detail here is maybe similar to what you saw in Gabriel's talk earlier today. Here we're dealing with a different broken symmetry, so we're displaying it in a different manner. But to some degree, we're getting at similar physics when we're analyzing our images. I'll note that in these images, we can sometimes identify topological defects, not just domains of various types, but also topological defects. So here, for example, is one image where I've deconstructed the image in terms of the orientation of the magnetization and also the magnitude of the magnetization. And within a portion of the image, we can see that there's a point around which the magnetization wraps around by 2 pi through a region where there is non-zero transverse magnetization. So we can identify this particular topological defect as something known as a polar core spin vortex, and we've done a number of experiments where we can see several of these vortices that emerge through quantum quench. We have not done the gorgeous experiments that Gabriel showed this morning on watching the dynamics of these vortices in time. That's something that we have wanted to do, but haven't really had the signal to noise to do yet. Now, this gives us an opportunity to study a little bit more the dynamics of how this symmetry breaking occurs within a fairly closed quantum system. It turns out that there's a way of characterizing the symmetry breaking in this system in terms of the parametric amplification of quantum noise. So let me remind you of the paradigm for how to understand parametric amplification. You can think about the physics of a simple harmonic oscillator, which initially has some distribution of uncertainty. Let's say this is the Wigner function in the plane that is in its phase space plane that is spanned by position and momentum. If I take this harmonic oscillator and I suddenly invert the sign of the potential energy, so the kinetic energy is still positive, but the potential energy is now negative, then this is, you know, a marble that rolls off the top of a hill and it undergoes a dynamical or a parametric instability. And that parametric instability is phase space preserving. It leads to a great amplification of some aspect of the motion of the object that we're describing. The fact that this is greatly amplified can be regarded as the fact that these initial microscopic fluctuations of the vacuum state are amplified into macroscopic fluctuations of now a macroscopically observable parameter. At the same time, because this dynamics is phase space preserving, we expect also there to be a suppression of fluctuations around an orthogonal dimension. So macroscopic symmetry breaking should be accompanied also by a reduction of fluctuations in some orthogonal quadrature. And it turns out that when we analyze the system in terms of the spin dynamics, we can identify what are the measurable parameters that correspond to position and momentum, but now in terms of the spin operators that describe this gas. Without going into detail, the two operators are one component of the transverse magnetization of the gas and one component of the magnetic quadrupole tensor of the gas. So we wrote up this work as a theoretical work to help us understand experiments that we were hoping to conduct in our laboratory. But then it turned out that other labs had much better tools to carry out the experiment. So I was happy to see, for example, this work out of Mike Chapman's group at Georgia Tech, which measures in the correct phase space. So he's measuring indeed the correct operators that I mentioned in the previous slide. He's able to measure after such a quantum quench both the creation of this macroscopically distinct state and also the suppression of fluctuations around an orthogonal direction. So this is, if you will, what happens when you take quantum quenches, which maybe come out of condensed matter physics, and you give them to atomic physicists who like to think about quantum information and quantum optics instead. They pay attention to this suppression of fluctuations, these strong correlations that can be maybe even used for measurement in the future. And there's very nice work also coming out of several other groups on this same topic. Our own experiments were conducted in on a large system, which is rather described sort of as a multimode version of that same parametric amplification. So the way to describe it in the case of our continuous quantum system, which is where we did our experiments, is that the gas has something like a harmonic oscillator at every wave vector of excitation that is possible. And as we quench the system from the paramagnetic phase to the ferromagnetic phase, what we're doing is we're changing the spectrum of spin fluctuations from being ones that are like a stable harmonic oscillator, where, for example, the squared energy of the oscillator or the squared frequency is always positive, finally turning into one where the squared energy goes negative within some range of modes that the system supports. So, for example, a gas that is quenched down to this value of the quadratic Zeeman energy would show these kinds of parametric instabilities for a wide range of k vectors, with a gain, which is given by how negative this squared energy is, which gets larger and larger as we increase the quadratic, the separation, as we increase the distance from the transition point. As we quench deeper, we see that now the spectrum also acquires a characteristic length scale, where the instability has its largest gain, and we therefore expect quenches down to these values to lead to patterns that have a characteristic length scale that's given by the amplification process. We've seen some aspects of exactly this description in our experiments, where we can apply this kind of quantum quench to different values of the quadratic Zeeman energy, and we see the consequences of this spectrum of an amplifier that is applied to quantum noise, turning into a macroscopic spin signal that has length scales that vary from long to short. We have, at least in our experiments, not yet been able to really connect these fluctuations that are seen after the quench definitively to quantum fluctuations that may have existed before the quench. So doing that quantitatively has just been too difficult for us to do in a multimode setting to this point. Now, I don't know if you guys are able to hear me and if you're able to ask questions. Maybe somebody from the control booth can talk to me about that. But I will just go on. I hope you're listening.
Yeah, I can hear you. Maybe I can ask, are there any questions now? Just a second.
It's just a technical question about those images. You're demonstrating the images everywhere, but is it a CCD image, or is it a computational result somehow? Is it integrated along Y?
Okay, good. Thank you for that question. That must have been unclear. So again, we have a gas that is, let me see if I can go back far enough. Too far. There's the surfboard. Good. So yes, you were right. So there's the y direction, which I've indicated in this graph, which is the thin dimension of the gas, which is typically between 3 and 5 microns in thickness. And then there are these two broad dimensions of the gas. This is just the nature of the container in which we hold our atoms, which are fairly broad in both the image directions. So what we do is we pass light through this surfboard of atoms, and then we image that light onto a camera. Now to turn, the set of images that I showed so far were based on circular optical birefringence. So the idea is that if I send circular polarized light through the atoms, the circular polarized light will acquire a different phase shift depending on whether the magnetization points in the direction of the helicity of the light or against the direction of the helicity of the light. And then I need to think of an imaging method that turns that phase shift on the optical field into an intensity pattern on my camera. And there's a couple of ways to do that. One is to use phase contrast microscopy. Another one is to use polarization rotation measurements using a linear polarization as the input. In either case, that turns into an image onto a CCD on my camera, which I can interpret as either the density plus something times the spin, or in another case, just something times the integrated spin of the atoms along the y-axis imaged onto the camera. Now, to get images that have as much detail as this, for example, we have to take several images of the same gas, because in one image, maybe we want to measure the magnetization along y, and then another image, I want to image it along x, and later along z. And the way we do that is between one dispersive image and the next, we apply either RF pulses or we apply magnetic fields so that the magnetization of the gas rotates from one image to the next. And then I can, through a series of these kinds of images, ask my computer to reconstruct an image that shows two resolved directions, but three resolved components of the magnetization of the gas. Is that clear?
Yeah. Any more questions? Okay, so please continue.
Okay, good. Now getting on to some more modern research in my group, we've been studying the elementary excitations of spinor-Bose gases. So I talked in the context of interactions, I talked about the rotational symmetry of the spinor-Bose gas. That is something that allows us to understand its interactions when it's still a rotationally symmetric situation, if we haven't strongly broken symmetry in some explicit manner. Now, as you all know, when you have a system that possesses a continuous symmetry, and then in its ground state, it breaks that continuous symmetry, that implies often that there are gapless excitations in the system, which correspond to spatiotemporal variations of the broken symmetry of the system. So for example, in a ferromagnet, I can have an excitation where a uniformly magnetized system now acquires a magnetization that varies as a function of space. And at very long wavelengths, I can argue that that excitation of the system has hardly changed the energy of the system, because at least locally everywhere it looks fairly uniformly oriented. And as a result, that introduces a gapless Goldstone boson, a certain excitation mode into the system. So since we're talking about ferromagnets, it makes sense to talk about magnons. And indeed, ferromagnetic spinor gases have Magnon excitations, which are spatial and temporal variations of the magnetization of the gas. Those excitations ought to be gapless, unless there's something that breaks rotational symmetry, and they also ought to be quadratically dispersing. That is a function of the particular symmetry breaking that we're talking about here. We've done a number of experiments now where we study these Magnon excitations, both in terms of their coherent dynamics and also in terms of their thermodynamics. The way we can introduce magnons into the system is simply by having a gas that is initially in its fully magnetized ground state, and then applying some kind of external influence to rotate the spins and therefore populate the gas with a population of magnons. We can have these magnons introduced either in a rather uniform manner by rotating all of the atoms by the same angle. This is something that allows us to characterize the magnon at zero wave vector. Or we can use, it turns out we can use circular polarized light to apply what is effectively a local magnetic field, a fictitious magnetic field, at a particular location within the atomic gas, and that produces a localized Magnon wave packet, if you will. If I want to characterize the evolution of these magnons, there's a handy trick that I can apply. If I start off with a gas that is, for example, all magnetized within one magnetic sublevel, and then I apply a small rotation to the magnetic moment, which introduces magnons into the system, we see that the first order effect of that rotation is to take a small population of atoms from this dominant Zeeman level to this now subdominant Zeeman level. And the population of atoms in this m equals 0 state for low Magnon density is in fact directly representative of the density of magnons in the system. So if I can just spatially resolve the population of this Zeeman distribution, then I have a spatial resolution of the density of the magnons I've introduced to the system. So here I'll just provide a little bit of detail. And again, I think Gabriel described a little bit of these tricks in his talk this morning as well. Our task is to make spatially resolved images of the population of atoms in these three magnetic sublevels. And the way we do so is we apply a brief microwave field that can be tuned in frequency so as to drive, let's say, just a few atoms out of this magnetic sublevel. Now these atoms are in the F equals 2 manifold of the ground state of rubidium, and I can image them. In this case, I image an absorption image, like what Gabriel showed this morning. And this absorption image represents an in situ distribution of the atoms within this magnetic sublevel. After the imaging is done, these atoms fly away. They become quite heated by the imaging pulse. And that allows us to now probe the gas again. And we probe it a second time. We can apply a microwave pulse that, for example, samples this magnetic sublevel instead. And then I get an image of the m equals 0 atoms, which is the same as the distribution of magnons that maybe I've applied to my system. We can complete this process with more pulses. We can image lots of information about the quantum gas in a fairly non-destructive manner by doing this. This method of analysis has allowed us to study the coherent propagation of magnons that are introduced coherently into the system. So that was what I was showing you in this set of 3 images by which I exemplified the imaging process. If I think about this distribution of magnons, which incidentally I imprint into the system by shining 2 beams of light onto the system, which interfere at the location of the atoms. This distribution of magnons is composed of 3 wave packets of magnons, or magnons at 3 distinct momenta. There's magnons that are stationary, magnons that are moving down, and magnons that are moving up. Because the moving magnons have a different energy than the stationary magnons, I expect this magnon distribution to evolve in time. And the evolution in time will display for me the recoil energy of the magnon, the difference between an energy between a stationary magnon and a moving magnon. And in fact, that's what we observe. We find that the magnon distribution oscillates in time, and the oscillating feature is the contrast of this density distribution, of this density modulation. We find that as a function of time, the magnons are first amplitude modulated in their wave function, and then phase modulated, which means that we don't see a contrast in the density pattern, and then amplitude modulated again, and so forth. And so from a set of images like this, I can follow the evolving magnons in time and measure the recoil frequency, which is just the oscillation period or the oscillation frequency that I see in these data. So this method allowed us to measure the Magnon dispersion relation really quite precisely. We were able to confirm that it indeed is quadratic over the range that we measure in momentum. With that quadratic dependency, we were able to characterize the effective mass of the magnons. And we found, to our surprise, that the magnon is about 3% heavier than the bare atom. We weren't expecting a 3%, I mean, 3% sounds like a small number, but we weren't expecting a shift of the magnon mass by 3%. We were expecting at most a shift of the magnon mass by 3 parts per thousand. We still don't quite know what has caused this mass shift. I think some theorists are still chewing on the idea, but we're really uncertain what it is. More recently, we've been looking at the physics of magnons after they've stopped propagating coherently and when they form now an incoherent gas of magnons. And it turns out that we can, by producing an incoherent gas of magnons and then cooling our spinor gas systems, we can study another phase transition that occurs in these systems, which is Magnon condensation. Many of you are a solid-state physicists, so I think you know pretty well that Magnon condensation is a useful concept in solid-state physics to describe either equilibrium or non-equilibrium phase transitions, which, when they occur, they manifest as a sudden breaking of some transverse rotational symmetry of the system. So we can study a similar dynamic within our cold quantum gas. And here's how the experiment occurs. We take a gas of atoms that is Bose condensed up at, let's say, this temperature or this depth in the optical trap. We now introduce magnons into the system, and we can introduce whatever number we want. We wait for a while. While we're waiting, we apply a bit of a magnetic field gradient, and that seems to allow the magnons to cease propagating coherently and eventually to thermalize into just a non-degenerate gas of magnons that reside within the otherwise ferromagnetic Bose condensed gas. Now we can lower the temperature of the gas by lowering the depth of the trap that holds the atoms, and that let's say that reduces the critical number for Magnon condensation until it is now below the number of magnons that we have in our system. And at that point, we expect the magnons to undergo Bose condensation. So let me tell you what the findings are. One thing is that we observe the Magnon condensation phase transition. And what's interesting about this is that the magnons, even though they're held in an inhomogeneous container, the magnons within the superfluid gas behave as if they're in a completely flat box container with no variation in the potential energy. That's, if you will, because magnons are gapless. Everywhere within the equilibrated gas, they have, to create a magnon costs you no energy above the chemical potential of the system. And since at equilibrium, the chemical potential is constant across this condensed gas, then so is the energy of a magnon when it's stationary. So that was an interesting finding. Another one was that Magnon condensation, when it occurred again very inhomogeneously. So here are some images. Again, I'm showing you the transverse magnetization of a gas after it's gone through the Magnon condensation phase transition. The color scheme is the same as the one that I used earlier. And you see that, yet again, the gas is very inhomogeneous in its transverse magnetization. It clearly shows a strong transverse magnetization due to Bose condensation of the magnons. But that transverse magnetization is very inhomogeneous, both in amplitude and in phase. This denotes the fact that the Magnon condensate order parameter is very inhomogeneous in these experiments, and in fact remains inhomogeneous for the entire duration of our experiment. So that's an interesting dynamics that we still need to understand in our system. Okay, so I've talked for much longer than I would have wanted to about the topics so far, which leaves me almost no time for the last part of my talk. Let me ask the audience and organizers how you'd like me to proceed now.
Officially, you'd have 5 more minutes. So if you want to allow time for questions, I'd say you can go on for, I don't know, just 2 more minutes, and then we turn to questions.
Okay, then I will only very briefly tell you what this would have been about, which is the physics of spin excitations as they're influenced by light. So since your conference is on non-equilibrium quantum physics, I think it's interesting also to consider quantum physics that occurs in a system which is driven and dissipative. So we've done a number of experiments now where we trap a cold gas of atoms inside of an optical cavity. And we use light that shines into the cavity to both measure and then also influence the degree of freedom that we're trying to sense. Some of these experiments have been in the realm of optomagonics, where the degree of freedom of the atom that we interact with is their motional degree of freedom. More recently, the experiments we've done have focused on the spin degree of freedom of the atom, where we can sense the magnetization of the gas, basically using the same methods that we used earlier to image the gas. Now we're using it within an optical cavity to affect the magnetization dynamics and also to measure them in real time. And so just to summarize what we see in this system, we see, first of all, that we can, by connecting our spin to an optical field, we can stabilize the spin in a non-equilibrium configuration. And so that, in our case, for example, we can drive the spin to a state of negative temperature instead of positive temperature. A second thing we see, and I know this is too fast to understand, a second thing we see is that if we create a system where there's actually 2 degrees of freedom that are being acted upon by the same optical field, but where one of these degrees of freedom is a mechanical degree of freedom, which has positive mass, and the other one is a spin degree of freedom, which we can place in a negative temperature state, then when we shine light into the system, it causes a coherent coupling between these 2 harmonic degrees of freedom. And it leads quite generically to something known as the negative mass instability, which occurs whenever you couple one oscillator with a standard Hamiltonian with another harmonic oscillator where you've taken the Hamiltonian and stuck a minus sign in front of it. So let's say that's an inverted mechanical oscillator whose mass and also potential energy have a minus sign in front of them. And that turns out to generically lead to a parametric instability that produces very strong correlations between the 2 degrees of freedom that are coupled. And we're able to image those correlations with fairly high precision by looking at the output of an optical cavity, which is used not only to create the coupling which leads to the instability, but is also used to read out the correlations that result from that instability. Okay, that was too fast to understand, but that's what I would have told you. Let me get to just to these final thoughts, which maybe can inspire our conversation. First of all, I think the work that we've done in my lab, the work that Gabrielle has shown earlier today, the work that's going on in a lot of laboratories worldwide, shows that quantum gases are a really delightful laboratory in which we can explore basic ideas in non-equilibrium quantum physics, because we can create conditions where interesting quantum dynamics occur and where they persist for very long periods of time. So, you know, the more ideas we come up with from a theoretical perspective, I'd say the more we should all be talking to cold atom experimentalists and getting them to try to exemplify and then explore those ideas more deeply experimentally. That might move the entire field forward rapidly as it's done so far. A second thing I want to emphasize to an audience that is thinking about non-equilibrium physics is that there are many flavors of non-equilibrium physics. Non-equilibrium is simply what isn't equilibrium. So there's obviously many ways of having a system not be in equilibrium. A lot of the discussion has focused on quenches. For example, that's one of the key words in the title to the workshop. A quench is thought of as a system which has a constant energy-preserving Hamiltonian, is placed in a non-stationary initial state, and then is allowed to evolve. So that's only one paradigm for non-equilibrium quantum physics. It's interesting, but it's not the only paradigm. There's a lot of thought now going into non-equilibrium physics that occurs in a Hamiltonian system, which is periodically driven in time. So, does this kind of Floquet-driven quantum system, does it have an effective low-energy theory that describes it? What do quenches look like within Floquet systems? What kind of topological character can you have in a Floquet Hamiltonian that is different from the pieces of the Hamiltonian that are being modulated in time? So that's all very interesting within non-equilibrium physics. I referred very briefly to experiments that show my own group's interest in non-equilibrium quantum physics within systems that are open, that are deliberately open, where information and energy can flow in and flow out of the system. If you will, that is, real-life quantum mechanics. Every real quantum system is open. But I think also from another perspective, from a scientific perspective, I think we understand open quantum systems only at a very, very simple level. I think we understand them at the level of a single mode, a single cavity, a single transmission line. But we don't really understand the full range of phenomena in driven dissipative systems if we're talking about many-body quantum physics. And that is a big challenge for the theoretical field, I believe, and also one where cold atom experiments can have a lot to say in the near future. Lastly, a system that is open also allows the experimentalist to change the Hamiltonian in time. So now we have a different context for non-equilibrium quantum physics, which is what happens when I take a many-body quantum mechanical system and I place it within a feedback loop? What's possible in these situations? So for example, if I think about quantum magnetism, we're often interested in a particular model Hamiltonian because it has a ground state that is very interesting, like maybe a spin liquid or something that would be really interesting to observe. But why should we focus on equilibrium states? If it's the state that we're interested in, shouldn't we, within any Hamiltonian, instead come up with a feedback mechanism that stabilizes that state and just produces it for us to study and make use of? It's a different way of approaching many-body quantum physics. I think we have some ideas for getting this started within our own experimental setup, but I think it's going to take off in the coming years and find application in a lot of experimental systems. So with that, I will conclude. There's a number of stuff that I did not tell you about that's going on in my experiment. So you can ask questions about that, but probably there are enough questions on the topics that I raised, so maybe we can ignore them. Lastly, since this is the International Institute for Physics, I want to mention that there are several efforts now to place ultracold atoms up in the free fall of space. There's a laboratory that is due to be launched later this year. There's another one due to be launched maybe several years later. Both of these are instruments that will be placed on the International Space Station. And it is potentially possible that any scientists, both in the United States and Germany and elsewhere, will be able, there will be a vehicle for them to submit ideas for what to do with these instruments and have them operate as a user facility. So, I recall that, we saw these beautiful data this morning about superfluid hydrodynamics within quantum gases. And I recall that one of the most interesting space experiments had to do with the lambda point of liquid helium. You know, what really far out ideas can we realize in a free fall environment where atoms can propagate for very long periods of time, where they don't sag under gravity, and where we can get rid of inhomogeneities of the system. So think about that. And if good ideas come up, I'm in a position to submit some of them to the definition of some of these missions. And I'd be very happy to hear your thoughts. Okay, so now let me really finish. Thanks a lot for your attention.